Hello students, in this week's video, we'll be solving some problem sums that involve us having to find stationary value or stationary points. So do get ready a pen and some papers and practice along with me. Let's look at some important concepts. Supposing you're given y equals to f of x and you're told that y has a stationary value or stationary point, so what does it mean? I'm going to use a diagram to illustrate it. Supposing if you have a curve that kind of goes this way, and if you notice that at this point here, right, if you were to draw a tangent line, right, so this tangent line is actually a horizontal line. And what is the gradient of the horizontal line? Yes, the gradient of that horizontal line will be equals to 0. So let's look at another point. If you will see that there's another point here, that we can draw a tangent line. A tangent line is a line that cuts only the point at, cuts the curve only at one point, and that tangent line, you can see it's the horizontal line, and that is when the gradient of horizontal line is equals to 0. Right, so why is it called the stationary point? Because if you were to trace the curve, you imagine you are somewhere here and then you travel all the way up here. When you reach the highest point, basically you will just like stop there for a while before you proceed further down. So you can actually compare this with riding on the roller coaster, right? When you ride to the highest point, you stop for a while before all the screams come in. So all these points that you paused are called stationary points. And that is when you can draw a tangent line which is horizontal to the x-axis. And that is when your dy dx is equals to 0. Let's look at what are the different types of stationary points. The point could be a maximum point, as what I've illustrated in the earlier slide. It can be a minimum point. It can also be something called points of inflection. So how does point of inflection looks like? So why is it called a point of inflection? Right, let's examine this curve here. Right, if you were to consider this part of the curve, point C is considered a maximum point, right, for this part of the curve. However, if we were to examine the other part of the curve, then that particular point here is no longer a maximum point, it's a minimum point. So when you have points like it's maximum for some part of the curve and minimum for another part of the curve, we call this a point of inflection. So it is possible for a curve to have a few stationary points. Right, and then so it's our job next to find out, to determine all the stationary points, when we let dy dx equals to 0, all the stationary points that we have got, what are their nature? Are they a maximum point, a minimum point, or a point of inflection? So the next slide, we will learn how to determine the nature of all these stationary points that we have found. So in this slide, we're going to learn how to determine the nature of the stationary point. So there are two ways of determining the nature of the stationary point. We can use the first derivative or the second derivative. So in this slide, I'm going to show you how we can actually use the first derivative to determine the nature of the stationary point. So supposing I have, after using dy dx equals to 0, and I found the values of x to be equals to 1. Right, so I have a point x equals to 1. But I'm not too sure that point, is it a maximum or minimum point? So what I'm going to do next is okay, x equals to 1, we all understand, we get it by using dy dx equals to 0. So the gradient is a horizontal line, right? The gradient of that tangent line, it's a horizontal line. So what we're going to do next is that if I can determine how the gradient of a point that is on the left side of x equals to 1, if I can determine how the gradient is like, supposing the gradient is a positive one, and then if I can determine another point that's to the right of x equals to 1, determine the gradient, and if I were to find that the particular point, the gradient is negative, and if you join all these three gradient ups, you can see that what you're getting is a maximum point. Right, so this is what we're going to do. All right, we're going to examine the gradient of a point that is to the left of x equals to 1 and is to the and the right equals to x equals to 1. So this particular point cannot be too far away from x equals to 1. It cannot be too far, because if it's too far, then it's not accurate. So what we're going to use is just going to use take x equals to 1 plus minus 0.1. That means on the left, you just take 1 minus 0.1. And on the right, you just take 1 plus 0.1. So we're going to use the 0.1 as a guide to find these two important points. To find the gradient of these two important points. So this is what we're going to do. All right, so 1 minus 0.1 to give us x equals 0.9. And you're going to substitute x equals 0.9 into your dy over dx, whichever gradient functions that you have found, okay, after differentiating your y. And if you happen to get the value to be negative, means you're getting a negative gradient, right? Negative gradient. And how do you draw a line with negative gradient? Yes, you will look in this direction. And of course, x equals to 0.1 will give us our gradient equals to 0. That's the horizontal line. And then we're going to take 1 plus 0.1. And if you substitute into your gradient functions, if you get a positive value, this is how your tangent line will look like. And if you join all these three tangent lines, you will form a minimum point. Okay, so this is how you use the first derivative to determine whether the point is a minimum or a maximum. Let's look at how the maximum looks like. So we use a similar concept. Okay, use a similar concept. We let x equals to 0.9, and if you find out that the gradient functions, whatever dy dx you have, it's a positive value, this is how your tangent line will look like. And of course, the x equals to 1, that is where you get your dy dx equals to 0, horizontal line. Okay, and then if you join them up, you will get a maximum point. Right, so this dy dx I'm talking about for the first and second case, of course, is different value lah. That's one. This dy dx is different from, I'm just giving you how you can go about finding it. Of course, there are different dy dx. That's why in the first case, you can get less than 0. Second case, you get more than 0. Okay. It can also be points of inflection, like what I mentioned earlier on. So how do you get points of inflection? That is when the point on the left gives you a positive gradient, the point on the right also gives you a positive gradient. And if you join all these three together, you get a point of inflection. You basically get how something like this. Okay, right. It can also be both of them are negative on the left and on the right, and it will look the curve. If we were to join them, right. So in this slide, we're going to use the second derivative to determine the nature of the stationary point. So what does second derivative means? Basically, you just differentiate your dy dx. That means you differentiate y 2 times. So supposing given the stationary point at x equals to a can be any constant. And if you're given a function y equals to f of x, and you have a stationary point at x equals to a, right? So you just differentiate the dy dx again to get your d squared y over the x squared. And if that value come up to be less than 0, then P is the maximum point. And if that value come up to be positive, then P is the minimum point. But there's a catch here. What is the catch? If the value come out to be d squared y over the x squared equals to 0, it is inconclusive. Which means you cannot use this method to determine the nature of a stationary point. So you have to fall back to using the first derivative. So this is the catch. So this is something you have to remember. Right, we're going to move on to exercise 14.2. So are you ready? Right, so for 14.2, the problem sums, the questions are really problem sums. If you look at question 5, you can see that it's more lengthy, more information given to you, and it requires you to provide more workings than what we have done when what we have done for the questions is 14.1. So in questions 5, we're given a trapezium, all right, and yeah, trapezium have all the dimensions given there, and you're told that the perimeter of the cupboard is 24, right, and you asked to find the expressions for S. S represent the area, okay, in terms of X. And for part 2 is to find the maximum value of S, explaining why this value is a maximum. Alright, so for part I, we'll just go ahead to find the perimeter of the cupboard first. So perimeter meaning we have to find all the dimensions. So if given PQ, PS, of course SR will be Y centimeter, RT. The only one that is not given is QT. Okay, and you know that QRT is the right angle triangle. And therefore you can actually use Pythagoras theorem to find QT. Alright, so which is just basically RT squared plus QR squared square root it. So that's 64 squared plus 36x squared gives you square root of 100x squared. And that gives you 10x. Okay, so now we have all the dimensions given. So this is 10x. Centimeter, we can just basically add up all these dimensions and equate it to 24. Okay, right, so 24x plus 2y will gives you 24. And you can divide by 2 throughout, right, to get 12 minus 12x. So we're going to keep that. Why we want to keep that? Because we need to find expressions of S in terms of X. So S represents the area of a trapezium. So if we were to recall area of a trapezium, to find area of a trapezium, the formula will be half times sum of the parallel sides multiplied by your perpendicular height. Right, so therefore area is equals to half. This one are your two parallel sides. So which is y, this is y plus 6x. The perpendicular height will be this one here, 8x. Right, so if you simplify it further, you're going to substitute your y to be 12 minus 12x. So there's 2y there, y plus y is 2y. So basically it's just 24 minus 24x plus 6x. How do I get a 4x here? That is when I take half times 8x. Half times 8x gives you 4x. Okay, and then we're going to simplify it. Okay, simplify it as what? What I mean by simplified it means 4x 24 minus 18x. So you just take 4 times 24 gives you 96. 4 times 18 will give you 72x squared. Okay, so we're going to differentiate it. Why differentiate it? Because you are told in part 2 that s has a maximum value. So when you're told something like s has a maximum point or s has a maximum value, it means the s over the x is equal to 0. Okay, maximum value of s means the s over the x is equal to 0. Right, so you equate 96 minus 144x equals to 0. You find x to be 2/3. Okay, but we are not done yet because we need to explain why this value x equals to 2/3 will gives you a maximum value. So to do that, we need to use the second derivative. Alright, use a second derivative means you differentiate your ds over the x one more time. So you differentiate 96, you get 0. Differentiate negative 144x, you get negative 144. And of course, negative 144 is less than 0. So therefore, what you're getting is a maximum value. So how do you present it? So this is how we do it. X equals to 2/3 gives s a maximum value. And we're asked to find this value. So we need to substitute x equals to 2/3 into here to find the value of s. Which is 32 centimeters squared. So therefore, if you want your trapezium, the cardboard, okay, the cardboard that you use to make your trapezium, if you want the maximum area to be 32 centimeters squared, then the value of x has to be 2/3. Which means your PS will be 8 times 2/3. Then to find the values of y, you just substitute x equals to 2/3 into a parameter. No, don't need parameter, into here. Right, so you have the values for x, value of y, and with that dimension, you can make a cardboard in the shape of make a trapezium using cardboard, having maximum area 32 centimeters squared. Alright, let's look at question 6. So for question 6, there are three variables there, three variables x, y, and z. So the first equation is x to the power of 4, y equals to 32. Second one is z equals to x squared plus y. So if you look at the questions, you'll see that they phrase it such a way that in part I, you're asked to find z in terms of x. And then in part 2, you're told that z has a stationary value and show that this value of x, in part 2, you asked to calculate the value of x for which z has a stationary value. So you can see that in part 2, we are supposed to find the z over the x. The z over the x, z has a stationary value. So the z over the x, and that's the reason why in part I, we are asked to find z in terms of x. So what we need to do is just to make y the subject from the first equation, substitute into the second equation, and that's it. Okay, and we need to write that as a negative index to help us apply the power rule in part 2. Okay, and then we're going to equate it into 0, because for stationary value, stationary point, we let the gradient function equal to 0, right? And of course, you have to put back, write 128 over x to the power negative 5, put it back as your positive index, that is 128 over x to the power 5. Okay, so I'm going to make just bring your 2x over to the other side, so I can just do a cross multiplication, cross multiply, to get 2x to the power of 6 equals to 128, and then divide by 2 on both sides to get x to the power of 6 equals to 64. So the next step is, how do I get x equals to 2? You just bring both sides to the power 1 over 6, because 6 times 1 over 6 will give you 1. So basically this is what you want. You want to find x, right? Which means you're finding x to the power 1. So 64 to the power 1 over 6, you can use a calculator, or you can find the 6th root of 64, which equals to 2. Alright, so the next part of the question is, okay, we found the value of x already, but that's still not enough. We need to show that this value make us give z a minimum. Then show that this value makes z a minimum. So that means we have to use either the first derivative or the second derivative to show that x equals to 2 will give z a minimum. So I'm going to show you using the first derivative, which I'm not too sure why I did it. I should have just gone ahead use the second derivative, but never mind. I'm just going to show you both methods, and then you can compare which one is easier lah. Okay, so the first method is using first derivative. So x equals to 2, so that's where your dz over the x equals to 0, so horizontal line. And then 2 minus 0.1, because we're using plus minus 0.1 as a guide. Remember, always remember that. Plus minus 0.1, so 2 minus 0.1 gives you 1.9. You substitute x equals to 1.9 into this one here. Use your calculator, you'll work out to a negative gradient. Which is how the line will look like for negative gradient. Then of course the z over the x equals to 0 is when x equals to 2 horizontal gradient. No, sorry, not horizontal gradient, horizontal line, horizontal tangent line gradient 0. And then 2 plus 0.1 gives you 2.1, right? Substitute into your dz over the x, you get a positive gradient. So if you were to combine all these three tangent lines together, it will form a minimum value, a minimum point. So but we're talking about value for z we're not talking about point value. So x equals to 2 will give z a minimum value. That means when you substitute 2 inside this equation here, you will have 4 plus 32 over 2 to the power of 4 is 16, right? So you can work out this value to be 4 plus 2 give you 6. So it's a value. It's not a point, it's a value. That's why x equals to 2 gives that the minimum value. So that's using first derivative. So if you're using second derivative, this is how you do it. Okay? Which you will get the squared z over the x squared to be 12, which is positive. So therefore x equals to 2 gives z a minimum value. So you decide which way you want to use, either the first derivative or the second derivative. Okay, let's look at question 7. So question 7, we are told that there's a curve, a cubic curve, and on this curve, so let's try to draw a curve. Okay, we don't need to draw exactly how the curve looks like. Just draw a curve can already, an arc, and then at this, there's a point P here, and of course tangent normal, it's good friend of a tangent line. So let's draw a tangent line first, and then with the tangent line, I can have a normal. So this is our normal line end. So what we are saying that because it's a line, so it has a tangent, it has a gradient. So the particular gradient, which is your dy dx, okay, is either a maximum or minimum. Which means your dy dx is equal to 0, which means my diagram is not correct. Because if you dy dx equals to 0, then it should be a horizontal line, right? Okay, let me try to draw a horizontal line first. Okay, so that is our normal. Okay, and to have a normal, we should have a tangent, right? Okay, so the curve may be something like that. Eh, wrong. Wrong. Let's draw, let's draw a, wait, so the normal, okay, this is normal, so this is tangent. So how do I draw the curve? Oh yeah, the curve could be something like this lah. Okay, the curve is something, so this is a tangent line. Okay, it kind of makes sense now. Tangent and normal is like that. Normal is horizontal. Okay, right. So what we're going to do is we're going to find dy dx first. Okay, and then if you were to remember how the connections of the normal and the tangent line, basically they're perpendicular to each other, right? So therefore the gradient of your normal line, it's -1 divided by the gradient of your tangent line. -1 divided by dy dx, right, will gives you gradient of normal line. Okay, -1 divided by the gradient of the tangent line give you gradient of normal line. Okay, so this is the concept we're going to work on. Right, so let the gradient of normal line be n, so therefore n is -1 divided by dy dx. Okay, and why do I change this whole thing? This whole thing is to power 1, right, to negative index, so that you can, let me use a chain rule. You can use quotient rule if you want to, but I think it's kind of waste of time, so I'm going to use chain rule instead. So my dn over dx will be, okay, if you bring the -1 down, negative times negative gives you positive. Okay, this one remain the same, and then -1 minus 1 gives you -2. Differentiate whatever that's inside, that will gives you 12x minus 24. Differentiate 1, you get 0. Okay, and then of course I'm going to change this back into positive form, because I'm going to let that equals to 0, so it's easier to work. By changing your negative index to positive index, you get a fraction, and when I let that equals to 0, you see what happened. I just do a cross multiply, and then the denominator will be gone. So leaving us only 12x minus 24 equals to 0, and x is equals to 2. Okay, right, but that's not the end yet, because we asked to find the coordinates of P. So we only managed to find the coordinates, the x coordinate. We still have to go on to find the y coordinate, so I need to substitute x equals to 2 into your curve to get the y coordinate. So therefore your point P is 2 bracket -21. And again, that is not the end yet, because, oh, I think that's all, because we are not asked to show whether it's a maximum or minimum. We are not asked to show. You don't see the word show, right? It's just telling you that, ask you to find the coordinates of P only. Okay, so that's it. We can stop here. Okay, let's do a question 13. If you're getting very tired and don't find yourself able to continue, just give yourself a break. That's what I did just now also. Okay, with all this explanation, I think it's killing me. Right, so if you look at question 13, we're talking about trapezium, and what do we want to do? It looks like Toblerone. Have you eaten Toblerone chocolate before? Yeah, so what we need to do is to, in part 2, zoom into part 2, you asked to find the value of x for which the cost of aluminium needed. Oh, because you need to wrap this prism. Imagine it's a chocolate lah. You're going to wrap it with aluminium foil, and of course you're going to save money lah. You're a big boss now. Think of it as you are a big boss. You're going to produce a lot of chocolates to sell, and you have to buy aluminium foil to wrap around this Toblerone chocolate. And of course you want to keep your cost a minimum, right? You want to earn lots and lots of money. So therefore, we need to find out the value of x. How big you want your chocolate to be, such that you just use as little money as possible to buy the aluminum foil, to wrap around your chocolates to make money. Okay, right. So for some of you don't quite get why we want to study maximum minimum point, maximum minimum value. This is one real life example. Okay, it's one good example. okay, of how we can make use of the concept to earn money. All right, so for the first part, we need to show the total surface. Yeah, you need to find the total surface area first, because the total surface area tell you how big the aluminum foil is, right? Isn't it? Okay, and you'll see that the triangle given is a triangular triangle. At both ends is a triangle, equilateral triangle. So equilateral triangle means the angle will be all 60 degrees, right? All sides are equal. Okay, how do you go about doing it? I've actually enlarged the chocolate for you. Okay, so volume, to find volume, it's cross area of the cross section times length. So what do we mean by cross section? Yeah, that is cross section. Okay, the two ends are this one also. These two are the cross section. Okay, and then the length will refer to this guy here. All right, so how do we find area of your equilateral triangle? Yep, half AB sine C, half AB sine C. So half times x times sine 60 times h. Sine 60 is a special angle, which is square root 3 over 2. So this question is challenging. Involve trigo, involve your special angle. Okay, yeah. Okay, so we're going to keep that. All right, we're going to keep that. Oh, we don't keep that because we're going to equate it to 12. Because see, you're given that the volume is 12 centimeter cube. So we're going to equate that to 12 because we're going to make h the subject. Why would I make h the subject? Because the two variable here, x and h. All right, so if you want to, we can only differentiate, remember, one quantity over a second quantity. You cannot differentiate one quantity over two quantity, it doesn't work that way. So you're going to make h the subject and keep that because we'll use that later. How do we use it? Because for part I, we need to find total surface area, right? So total surface area means I need to find the area of the two triangle plus the three sides. Okay, S stands for surface area. Right, so the two triangle, we already found area of a triangle here, half AB sine C, this one here, which is this value here. So this one times 2, because there are two triangle. Satu, dua, two triangle. Okay, and then plus y xh. How do you get xh? Is this one. Let me erase all this. This is x times h, right? X, h. And there are three of them. There are three of them. Okay, let me show you where are the three, okay? 1, okay? 2, 3. So there are three of them. So therefore, times 3 here. Okay, that simplified it. As in, we substitute h to be 48 over x squared square root 3. And then what do we get? How do I get this? This and this. Okay, we'll give you 2. Okay, this one remain the same. And then I'm going to rationalize this guy here. Rationalize times square root 3 at the numerator, square root 3 at the denominator. Okay. So that, you see, the square root 3 times square root 3 gives you 3. So the 3 and the 3 go off. All this go off. And of course, this one and this go off. So you're left 48 square root 3 and just x only. And of course, this term remain the same. Alright, so we have painstakingly show part I, that is to show that the total surface area is given by square root 3 over 2x squared plus 48 square root 3 over x. The next part of the question is, you are told that find the value of x for which the cost of aluminum foil needed is a minimum. Okay. Right. So to do that means we need to find the s over the x. We want to show that value is equal to 0. We want to have minimum surface area. Minimum surface area means we use as little aluminum as possible, right? So we're going to find the s over the x. So you differentiate it. And then this part here, again, change it to positive index. So changing from negative to positive index and positive to back to negative is very important. This concept is very important. If you have already forgotten how to do that, please revise. Refer to the earlier few videos. Let it equal to 0. Do a cross multiply. Oh, yeah, do a cross multiply. I skip one step here. If you do a cross multiply, you get 48 square root 3 equals to square root 3 x to the power of 3. And this can goes off. So you get x to the power of 3 equals to 48. So therefore, x will be cube root of 48, which is 3.63. Right, so this is what we need to do for part 2. Okay, we're not asked to show that it's a minimum. Right, they did not say show that it is minimum, so we don't have to do that. But for part 3, we need to explain what will happen if the cost of aluminum is, okay, if you don't use x equals to 3.63, if you use x equals to 5, or x equals some favorite number of yours, then what do you think will be the cost of aluminum be? Yeah, obviously, if you use some other value, then your surface area would not be a minimum. So of course, unless you want to make a huge toberon, you know, you're rich enough to make a huge toberon, you're not interested in making money, then of course you can just keep the cost. Oh, I actually went on to show that it is a minimum. But I don't think we need to show it, because in this question here, you just asked to find the value of x, for which the cost of aluminum needed to produce a container is a minimum. But if you want to play safe, all right, you want to play safe, it's not difficult just to show the value for d squared s over the x squared to be a positive value. So therefore, x equals to 3.63 will give the cost of minimum a minimum value. Alright, so if you present it this way, then that will give you perfect answer lah. But I don't think you are needed to show find the value of x for which the cost needed produces a minimum. You are not asked to show that it is a minimum. Okay, so I'm doing some extra steps here. Alright, never mind. So let's look at answer for part 3 as what I've explained just now. If x was arbitrarily chosen, that means if you use x equals to some other values than 3.63, then the cost of aluminum use will be higher. Because 3.63 is the minimum. Okay. Right, let's look at the last questions. Okay, so don't give up. Okay, we're at the last questions already. Don't give up. So for the last questions, you're asked to find the minimum distance. What is the minimum distance from a certain point 4,2 to the parabola? So parabola has many points, right? We don't know what particular point they're referring to. So let's just have one arbitrary point on the parabola. But let's see where 4,2 can be. So it can be there, right? And then we can just one arbitrary point on your parabola. I'll explain later how I get that point. All right, so we're going to connect a line from P to A. And we're going to show that this PA is a minimum distance. That means basically I need to find the distance PA, right? And differentiate it and let it equal to 0. Anytime you see minimum, maximum, minimum value, maximum, that means what we are saying is if I let the distance, since I let the distance be PA already, what we're saying is dPA over the X is, in this case is Y. I'm making in terms of Y. So dPA over dy is equal to 0. This is what it means. Okay, how do I get that particular point there? Basically, I just let your Y coordinate be Y. So if you let the Y coordinate be Y, then 8x is equals to Y squared. So x will be just Y squared over 8. That's how I explain how I get x to be y squared over 8. And then I let my y coordinate be y. I cannot let my y coordinate be a value. I cannot let it be 8, 7, 6, 5 or whatever. I cannot let it be a value because I don't know exactly where the point is. I can only make the point be in terms of y or in terms of x. I try letting it be in terms of x and it's horrible. The differentiation is horrible. So I will not advise anyone to let the x coordinate be x. I actually tried to do that, let the x coordinate be x. And then your y coordinate will be square root 8x. Okay. And then it's very tough after that when I need to find your distance PA. And also because I can have a positive or a negative, right? So to avoid that, okay, it's easier just to let it in terms of y. So let your y coordinates be y. Then from there you can find your x coordinate to be y squared over 8. So that explains how I get this point. And then from there you find that it's also easier to find the distance PA using distance formula. So you end up getting, simplified it to be like this. And since we're finding minimum distance means we need to find the PA over dy. That means I need to differentiate it. So to differentiate it, I need to convert this into index form. Okay, so I bring the half down. Let's explain this one. Keep whatever in the bracket remains in the bracket. Half minus 1 gives you negative half. Differentiate the one inside the bracket. So differentiate y to the power of 4 will be 4x cubed. Keep the 64 there, don't touch it. Differentiate negative 4y gives you negative 4. Differentiate 20 gives you 0. So we're going to simplify further. Okay, change this guy back into radical form, 1 over square root. And then simplify some more. Okay, why do I make this a fraction? So I can just multiply numerator, multiply denominator. Oh, we will look at it at the next slide. Okay, next slide, because I don't think there's space for us to do. Right, so we're going to let your dPA over dy equals to 0 because it's for stationary distance, stationary point, stationary value. Right, you just let the gradient function equals to 0. So this is what I have just now, right? So why I make it as a fraction? Because if you're going to draw a cross multiply, and you see that this goes off, this goes off, this goes off. So you only left this guy. And you will get here so you divide by 4 throughout. That's how you get y cubed equals to 64. So y will be cube root of 64, which gives you 4. Okay, right. So the next thing is when y is equals to 4, what happened? Your distance PA, we need to substitute into your PA, the distance PA, to get 2.83. And I think the questions require you to show that PA is a minimum. So to do that, we're not going to use second derivative. We're just going to use the first derivative because differentiating your dPA over dy is torturing. So using your first derivative, you show that what you're getting is a minimum value. So therefore, y equals to 4 gives PA a minimum distance.